All right, good morning. Okay, so reminder again, exam is this Thursday, 6:30 to 7:30 in Elliott Hall of Music. Be there 15, 20 minutes or so early at least, so you can get seated and settle down before the exam starts. So once again, make sure you look up where you're supposed to go. And also you need to know your 4-digit section number. Make sure you know that. If you forget, we'll remind you at the exam, but the more you know without being reminded, the faster we can get things going. All right. Exam will cover everything up to what we did on Friday. So what we're doing today is not on the exam. Okay? Okay, so we'll finish up 14.6 today on directional derivatives. So once again, this lesson is not on exam 1. All right, so last time we saw that if we have a function z is equal to f of xy, the directional derivative, capital D, under subscript u, the vector u, f is given by the gradient of the function f dotted with some unit vector u. And remember, the key thing is that this u vector has to be a unit vector giving the direction. Direction on which direction you want to move. And remember, the gradient, del f, is defined as the partial derivative of f with respect to x, comma, partial derivative of f with respect to y in the second component. So in the other notation, this is what we're looking at. Okay, so that's what we did last time. We already know this stuff. So today we're going to pick it up from here. We know that in general, the rate of change of f is going to depend on the direction that we move, on what the u is giving us. Okay, so we know that just by looking at the formula. Depending on what u looks like, the dot product will, of course, change in general. So a very, very natural question to ask is there a direction that we can move so that we always get the maximum rate of change? What is the direction that gives or that results in maximum rate of change? And we can analyze that question from just by looking at the dot product. Okay, let me do this on the next page. So first of all, let's revisit the dot product. If you dot two vectors, a dot b, remember you get the magnitude of a, the magnitude of b, times cosine of theta. where theta is the included angle between the two vectors. Okay, we know that. This is just one of the definitions of dot product. So now let's look at the directional derivative in the form of a dot product. Both of these are vectors. This is a gradient vector, and that's a unit vector. This, by definition, is also equal to the magnitude of the gradient vector, dotted with the magnitude of the unit vector u times cosine of theta. And once again, theta is the angle between the two vectors. Right? What's the magnitude of u? 1, right? It's a unit vector. So this is simply the magnitude of the gradient vector times cosine of theta. Okay? And we know cosine is always between -1 and 1. It'll get no bigger than 1 and no smaller than -1. So this means that the directional derivative f, the directional derivative of f is maximized when cosine is equal to 1, right? If this can only be between -1 and 1. So you want this to be as big as possible. You want to make cosine equal to 1. Cosine of theta equal to 1. And that means theta is equal to 0, right? In terms of the two vectors, what does that mean? They're parallel. The gradient vector and the unit vector are in the same direction. If the included angle is 0, they're in the same direction. In other words, this is telling us that the direction of the gradient vector is the direction to go to get the maximum rate of change. Maximum rate of change. And the maximum rate of change is the magnitude of the gradient vector. When this is 1, the rate of change is equal to the magnitude. And the max rate of change is the magnitude of the gradient vector. All right, so this is a very, very important result. Okay, so that's what the gradient vector tells you. So actually, it's a very, very crucial vector in terms of looking at the rate of change of stuff. And this will become the foundation of what we will need to do when we want to maximize or minimize a function later on. All right? Okay, let's do a couple examples. Let's find the maximum rate of change of this function at the point 0, 2. And we also want to know, once you get to that point, in what direction do we have to travel to get that maximum rate of change? All right, so we just saw that the maximum rate of change is in the direction of the gradient vector, and the rate of change is the magnitude of the gradient vector. So everything we need to know is in the gradient vector. Let's find that. This vector has all the answers that we want for this question. Fx, remember this means you treat x as a variable and y as a constant, right? So we get e to the y. Fy means we treat x as a constant, y as a variable. So therefore we get x e to the y. Let's find out what's going on at 0, 2. X is 0, so the second component will be a 0. And y is 2, so that's e squared up here. Right? And the maximum rate of change is the magnitude of the gradient vector. And that's e squared, right? There's only one direction, so the length of that one direction is going to be the magnitude. So what this is saying is that once you get to this point, no matter which way you turn, you will never find a rate of change that's bigger than e squared. It'll be exactly equal to e squared when you go in the direction of the gradient vector. And in what direction does this happen? Give this to me in the form of a unit vector. In what direction? 1, 0, or I, right? Yeah, absolutely. This vector only has one component, only in the I component. So if you want to give a direction in the form of a unit vector, then of course that's the I direction. Questions? Nope? Okay. What we just did is true for functions of 3 variables too. In fact, it's true for functions of any higher number of variables. For example, here we have a function of 3 variables. F of x, y, z is the inverse tangent of x, y, z. Let's do the same thing. Find the maximum rate of change and the direction of maximum rate of change. Okay, same thing. The gradient vector will have all the answers we want. Find the gradient vector, and we are done, right? Okay, if you remember the derivative of inverse tangent, we did that last week. Remember? 1 over that thing squared times the derivative of that thing. Yep. So, the inverse tangent of blah is 1 over 1 plus blah squared first. Then the chain rule kicks in. We need to take the derivative of blah. And the first one here, variables x. So what do I get on the top? yz. Very good. What about the second component? xz, good, over the same thing, right? All the denominators are exactly the same. And the last one will be xy over that. I'm sorry? X, yeah, that's a z. X, z, yep, good, sorry. yz, xz, and then xy. For the numerators and the denominators are the same. It's just 1 over whatever, squared. Let's give a point here. 1 to 1, yeah. Okay, then we figure out the gradient at 1 to 1. Downstairs would be 4 plus 1, so everything is over 5. Upstairs, yz, this is a 2. xz is a 1. xy is a 2. Maximum rate of change magnitude of the gradient vector. So let's see, we get 4 over 25 plus 1 over 25 plus 4 over 25 and this is a 9 upstairs, 3 over 5, right? That's the biggest rate of change we can ever attain on that surface at this point. So it doesn't matter in what direction you turn, you will never see a bigger change in terms of the fourth variable than that one. That's the absolute greatest we can get. When we move to a different point, we'll have a different maximum rate of change. But at this point, this is the biggest one we can get. And this will happen in the direction of the direction given by the gradient vector. So it happens in this direction. Is this a unit vector? No. How do I make a unit vector? Divided by that, right? So, yeah, well, it's a good idea to give your direction in a unit vector. So let's do that. Unit vector. So 2 over 5 over 3 over 5. That's 2 over 3, I think. 1 over 5 over 3 over 5 is 1/3, and 2 over 3 here. All right? So that's what the gradient vector tells you, how big the change is and in what direction that rate of change can be attained. Okay, this next example will do something a little bit different, but still along the same line. Find all points x comma y where the direction of greatest change of the function f of xy is equal to radical x squared plus y squared is I plus j. Okay, so this means that you have some kind of surface, but if you draw a bunch of level curves of that, we want to find out where on that two-dimensional space, essentially where the gradient vectors point in the direction of I plus j. Okay, now whenever you're dealing with the greatest change, you're dealing with something to do with gradient vector. If you don't know where to start, get the gradient vector and then find out what you need to do next. So here's our gradient vector. Derivative of this is 1/2 over this stuff to the 1/2 times 2x, so just x on the top. The 2's cancel. Same thing with the other component. Okay, so this gives you the direction of the greatest change. And we want so let me write that down. Gives direction of greatest change. And we want this to be in the same direction as I plus j. Right? Remember, we want the direction that gives you the greatest change to be I plus j. But now we found out the gradient vector is equal to this. And we want these to have the same direction. So what we do is we just set these two not exactly equal, but we want these two to be constant multiple of one another. Because these two things can have different magnitudes, right? This gradient vector is going to have a magnitude that's changing at all points. So we can't just set them equal to each other. Making them equal to each other, saying that they're exactly equal to each other. But we want them to have the same direction, but not necessarily the same length. So that's why this k is in here to adjust for that. Okay, so this gives you the direction of the greatest change. And we want this to be in the same direction as I plus j. But now we found out the gradient vector is equal to this. And we want these to have the same direction. So that's why this k is in here to adjust for that. because these may not have the same magnitudes. But they have the same direction. So you make them equal, but a constant multiple to adjust for the potential difference in the magnitudes. But magnitudes don't affect the direction. So the equality makes sure we have the same direction, but different magnitudes. Okay, then you look at that thing there. What we see is that if you make the components equal to each other, that's pretty much the only thing we could do. The I component is equal to the I component of the second vector, which is k. And the j component is equal to the j component of the second vector, which is also equal to k. And if both of these things are equal to k, then they have to be equal, right? So we're saying that x over radical that thing is equal to y over radical of that thing. But in this case, this also means that x is equal to y. So what this is telling you is that whenever x is equal to y on the level curve, f of xy is equal to some constant. The direction of greatest change is I plus j. Okay, so let's see what's going on here. All right, remember our function here. F of xy is equal to radical x squared plus y squared. What is the shape of the level curves? Not the whole surface, but each individual level curve. What do I get? Shape. What do we get for these level curves? Each one is a what? Circle, yeah? You make this a constant, then constant is equal to x squared plus y squared. So you get a bunch of circles. Each level curve is going to be a circle. So these will have different constants, so different heights coming out of the page. Imagine this is a mountain you're trying to climb, and these are different heights. X is equal to y describes a straight line like this. And what this means is that on any level curve you can find, whenever x is equal to y, when you're standing at that point on that level curve, if you want to have the greatest change in the value of the height, you will want to go in the direction of I plus j. Right? So if you're standing here and you want the maximum change of the height, essentially, coming out of the page, you want to go in that direction. So this is always the direction you want to go to get a maximum change. Now, when you talk about maximum change, this change can be positive or negative. So in this direction, you either get the greatest increase or the greatest decrease. And if you went in one direction, you found out you're getting decreasing function, then you go the other way to get increase. So this direction will tell you the maximum change. And typically, you go along one direction, you'll get an increase, and the other direction will give you a decrease. Make sense? Yes? Okay. Okay, now let's find out exactly for a general level curve, what's the relationship between the gradient and the level curve? Level curve where z is equal to some constant of your choice. Looking at the last picture here, it kind of looks like that these red arrows are perpendicular to the level curves. Kind of looks that way. And it turns out to be true for any shape. And we're going to find out the reasoning behind that. Okay, so here's how we can explain that, what we just observed. If you make z equal to a constant, then instead of a surface, we get a curve. And that curve is a space curve. R of t is equal to some function x of t, some other function y of t. And this can look like any kind of shape. Let's say it looks like that. And let's suppose it goes in that direction. Okay, remember, level curve has a direction defined by the increasing direction of the parameter t. So this might be t equal to 0, this might be t equal to, I don't know, 15 or something. So as t increases, there's a direction involved in the space curve. So the function z as a function of f x, y could also be written as z as a function of x of t, y of t, equal to some constant k. Right? Any level curve is given by f, which is originally a function of x and y, but x, y in turn are functions of t. So this is a very, very classic chain rule situation where f is at the top. F initially depends on x and y, but those two eventually also depend on t. Let's take the derivative of f here. Using chain rule, we see that df dt and we use a regular d because f ultimately depends on t only, but it has two intermediate variables. So it's a partial derivative with respect to x, and then regular derivative with respect to t, plus the other route, partial derivative of f with respect to y. When there's a split, remember you do a partial. When there's no split, you use a regular derivative. So that's in general the derivative of f. But because we set f to be a constant to begin with, derivative of a constant is 0, right? So there we go, we get a 0 here. Now check out this equation here. The equation, we got these two derivatives added together equal to 0. If we rewrite this in a vector form, this can be written in this vector form. Right? If you take the dot product of that, you get this back. So if you go revert, if you reinterpret that as a dot product of two vectors, then you get this guy dotted with this guy equal to 0. What's this first vector? The gradient. What's the second vector? R prime. And geometrically, what's R prime? What's its relationship to the level curve? It's tangent to it, right? So this is the gradient vector. This is a tangent vector to the level curve. And if you dot these two, you get 0. So what that says, I'm just rewriting that same equation here and put down a few notes. So this is the gradient vector. We identified that. This is the tangent vector, R prime of t. And if the dot product of two vectors is 0, that means they are perpendicular. So the gradient vector is always orthogonal to the tangent vector for any given level curve. In other words, no matter what the level curve looks like, it doesn't matter what kind of shape it got. At any point, This is the tangent vector. At any point, the gradient vector will always be perpendicular to the tangent vector, no matter where you go. If you are over here, for example, your gradient vector will always point perpendicular to that. So what this means is that if you, on the level curve, if you want the greatest change, you want to go in a direction that is perpendicular to the local tangent curve. If you're climbing a mountain and these are different levels of height, if you want to get to the top of the mountain or get to the bottom the fastest you can, you want to travel in a direction that is perpendicular to the level curve on every level curve. That way you'll get the shortest distance from where you are to the peak, or from the peak down to the ground level. Does that make sense? Yep. Gradient vector is always perpendicular to the local tangent vector. Okay, let me talk a little bit about what we'll do on Wednesday. Okay, so today we cover lesson 15. Remember, 15 will not be on the exam. Exam will cover everything up to what we did on Friday. And on Wednesday, we'll do in-class review. So I sent you by email, I think, 4 old exams to look at, right? 4 or something like that. Do as many of those as you can. And what I will do on Wednesday is I will pick out the topics that you should concentrate on, and I will find corresponding problems from past exam, maybe from those 4, maybe from other exams, to illustrate the topics I want you to concentrate on. And that's what I'll do in class on Wednesday. Sounds good? Okay, well, we'll finish a little bit early today, but that's fine. See you Wednesday.
If you need chapter 4, we have that today, and chapter 5.
MC is in the